it's my pleasure to introduce.
The following is a student presentation for the 2022 capstone projects at Portland State University. All images, videos, and music used are either created by our team or sourced from public websites and postings. My name is Connor Gorman, and I am the team leader for Team 10. Our team members are as follows: Forrest Kramer, the team recorder, Chad Butler, the project planner, Noemi Jimenez, our timekeeper, and the remaining members are Riley Pugh and Nick Cornejo. The ocean makes up close to 71% of the Earth's surface, so it's natural that we want to learn more about it. To do this, we started with the surface. We developed methods for travel, tools to collect information and observe, and better ways to understand the ocean and its properties. However, to deepen our knowledge, we needed to dive deeper ourselves. To accomplish this, we once again developed vessels and tools we could use to make these observations beneath the surface. As time moved on, new technologies continued to develop and become more available to us. Now we wish to implement those technologies to further aid our exploration and discovery. Our team has been tasked with creating an underwater device capable of locomotion within coastal environments. The device is to serve as a research platform for surveying and experimentation. It should be bio-inspired. Our clients expressed further needs for the device to be modular and adaptable, lightweight, and silent during operation. These needs expressed by our clients, though vague, gave us an outline on what goals we needed to meet. The primary needs for the device were as follows: bio-inspired designs, locomotion capabilities within coastal environments, modularity for adaptive use, quiet operation, and a compact size and weight. Through further communication, our team tried to get specifics where we could. How heavy is lightweight? What kind of experimentation do the clients have in mind for the device? Unfortunately, the clients didn't always have the answers we wanted, so it was up to us to interpret and translate the requests. We talked back and forth amongst the team and came up with quantifiable metrics where we could. These metrics would be used to define each need and determine if it satisfied them once tested. Now that our goals were set, we sent our specifications to our clients and received their approval before starting the design phase.
With the tasks defined and our goals set, our team was satisfied with our initial meetings and began moving forward with the project. However, our greatest challenge began to rear its head: communication. At first, communicating with our client and organizing meetups was difficult. Their schedules and ours did not align, and so we offered a solution. We would hold our meetings at a standard time when the majority of our team was available. We would then schedule supplementary meetings with the clients as needed, such as when the team had questions to ask them or the clients wanted an update about our work. One of the two clients approved, and we shifted our focus to developing the device, believing that we had an understanding about meetings. This decision was made in late October. Flash forward to the end of February. Over the few months, our team had asked our clients a few questions here and there, and we operated autonomously while we ironed out our design concepts. Our clients did not attend a majority of our meetings, nor did they express concerns on the matter during this period. Towards the middle of our term, our team had made enough progress that we thought it would be a good idea to reach out and update the clients. After seeing our update, the clients raised concerns and wished to meet to discuss our designs. During the meeting, the client who attended further expressed their partners and their own dissatisfaction with a lack of communication and concern about some of our design choices.
And a big reason I wanted to jump in here is Raul and I feel that you have not been communicating with us well enough. We're not quite sure what's going on, and we're definitely thrown off by some of the decisions that made in your email.
To remedy this, we created a presentation detailing each aspect of our design, the considerations made, and any supporting evidence we had. However, communication once again became an issue. After finding a time that would work for everyone involved, we let the clients know when and where we would be meeting via email. The client who most strongly expressed their disappointment in our communication did not respond to that email, and when it came time to the meeting, the same client did not arrive. Their partner quickly reached out to them at the start of the meeting and stated that because we sent a Zoom link as opposed to a Google Calendar link, the absent client either forgot or did not plan on attending the meeting. In our previous discussions about meetings and meeting times, neither of them had mentioned the requirement of a Google Calendar invite. Luckily, the absent partner was able to attend the meeting 30 minutes later. After the presentation of our current design and the reasons we had made those choices, we received a thumbs up and the understanding that we were good to proceed. We have since made it a habit of giving our clients regular updates, requested or not, and plan on meeting with them regularly so that they can provide input during the design phase, rather than asking for their approval after the choice has been made. Internal communication has also affected our progress, as the entirety of our project has been conducted during the COVID-19 pandemic. Our team relies heavily on virtual communication, which creates delay and room for interpretation between the team members. To address this, we have shifted to working together in person when possible so that each member is able to see a larger picture of the device and clearly see how to integrate their designs with one another.
Hi, my name is Forrest Kramer. I'm the recorder for Capstone Team 10, and I also work the propulsion and bodywork of the robot. Today, I'll be talking about the propulsion method used in our robot. One of the main requirements for our capstone was that the robot needed to be bio-inspired. The inspiration for this actually came before we even selected the capstone. I was reading a hard science fiction novel called Manifold by Stephen Baxter, in which a squid is genetically modified to be super intelligent and trained to pilot a spacecraft. The idea being that a squid uses jet propulsion naturally underwater, and this would translate to a natural ability to control a jet-propelled spacecraft. This led to a mild fascination with squids and cephalopods, and when the capstone projects were presented, a bio-inspired underwater robot jumped out at me, and an idea formed for a propulsion method. I discussed this idea with the team, and we submitted a bid for this project, among others. After we won the bid for the underwater robot, we discussed the idea further and worked together to refine it, and it became the backbone of our project. The idea is based on the way that a squid propels itself through the water. As you can see here, squids use a form of natural jet propulsion, where they fill a cavity in their mantle with water, and then expel it out through a small nozzle in order to generate force. They then use fins to control their direction and fine-tune their movement. Our adaptation of this propulsion method had several iterations, but the general concept remained the same throughout. We would intake water through channels inside of the robot and deposit it into a chamber where we get forced out through a small nozzle. Initially, we wanted to use a linear actuator in combination with a piston head to force the water out, but we ran into an issue where duty cycles prevented this method from being effective. The duty cycle here is the ratio between the actuator being active and non-active. Linear actuators tend to have high duty cycles due to the heat generated, so this really eliminated this option. We also toyed with the idea of using a Tesla valve instead of a check valve, but unfortunately we couldn't get that to work easily with the scale we were operating in. One idea suggested, to make the design even more bio-inspired, we should use a flexible membrane as a muscle. That would get compressed and decompressed rapidly in order to force the water through our outlet nozzle. After further consideration and discussion into the materials and the forces required, it was deemed too complex and inefficient to adopt purely in the name of bio-inspiration, especially as it came at the cost of performance. We spent a lot of time working with rotary actuators until it was discovered that it didn't fit within our size and budget constraints. So finally, we have fallen upon a much simpler method of using a simple DC motor, which will cause a piston to fire in a similar way that an engine piston does. This will allow for an intake stroke to pull water into the chamber with negative pressure, and then an outstroke to push the water through the nozzle and create a propulsive force. Our next steps over spring break and early next term will be to construct a test model for this design and work through any problems that may arise. An important aspect of this design is the nozzle that the water will get pushed through. In order to design this nozzle, we need to determine the most efficient nozzle ratio and outlet diameter. We settled upon a 5:1 nozzle ratio based on our research of underwater jet propulsion, and then did some calculations to determine our diameters required. The goal here is to ensure that the pressure at the outlet of the nozzle produced by our piston is greater than the surrounding sea pressure. To do this, we use this equation here. This relates the force created by the piston, the geometry of our nozzle, and the pressure at a given sea level. In this case, our unknown would be variable d, which is the diameter of the nozzle. Through the solution, we can find the minimum inlet nozzle required for our design in order to exceed the pressure of seawater at that depth, and with our 5:1 ratio, we can then use that to find the diameter of the outlet nozzle as well. Finally, one of the constraints provided with this project was the decibel level, and the need for a robot to be quiet. We were not provided with a specific decibel level, so we had to conduct some research in order to find an acceptable decibel limit. We finally established a limit of 60 decibels measured at 12 inches away from the robot. Unfortunately, it is extremely difficult to test decibel levels underwater, and the testing equipment required is very expensive. We asked PSU if they would be willing to obtain one that we could use, but this ended up falling through. So as a fallback, we used our ME411 project to conduct testing for this problem. We conducted some in-air experiments with the linear actuator used for previous prototypes, inside of a chamber constructed with the same carbon nylon composite that the robot will ultimately be made from, and compared several different soundproofing materials. All the materials tested put us at under 60 decibels, with the use of a car sound deadening mat being the most effective. All this will require further testing once we have a final design, and once we have determined a method to test the sound underwater, or an alternative comparison. Ultimately, we are making good progress with our propulsion design, and our next step is to select a specific motor that we can use and design a prototype to prove functionality before we can finally implement it into the final robot.
Hi there, my name is Riley Pugh, and I'm working on Capstone 10, designing a bio-inspired underwater robot. For most of the year, I've been working primarily on the design of the body. I'm on a team, a sub-team currently with Nick Cornejo, who's also working with me on the body, which he'll be speaking about it in a couple minutes here. I'm just going to talk about our main goals going into it and where our initial design came from. So going into this project, we knew the robot was going to be used primarily for collecting data underwater. We were told by our sponsors that it was to be bio-inspired. Quiet was another one of our main goals, as well as modular. So all of this is kind of research driven as far as the user being able to use the robot to collect data or whatever else they need to underwater. So the bio-inspired and quiet goals kind of come from that, because they're hoping to have a robot that doesn't disrupt the environment too much and doesn't scare off other sea creatures or just disturb things in the water, and they're able to get accurate data that way. And then the modular design also is another research-driven constraint that they're hoping that different sensors can be mounted to it depending on what they're looking to research. And so when we first started the design, we were focusing mainly on those three goals just because they were communicated to us as being top priorities. And also we knew it would be difficult because we had to think about things in a bio-inspired light, which is seemingly difficult. So when we first hit the drawing board, we were thinking mainly about the bio-inspiration. And so obviously we tried to figure out what animal we'd want to base it off, and we could have gone with a few different animals. We were thinking about octopi in the beginning, fish obviously, and then we decided a squid would be a cool animal to base it off, just because of the way that they move is kind of unique, and also would be a cool thing to implement in a robot. And so I'll put some videos of squids moving so you can see, but the main thing that stood out to us is that they use jet propulsion to move, especially if they're in a situation where they're scared and they need to get away fast. And squid have been clocked moving really fast underwater, so we knew it would be a good propulsion method just for moving the squid with enough force if it was a heavier robot. So that's where we got the idea for the squid design, and we kind of went forward with that and started throwing around ideas as far as taking this jet propulsion idea and kind of morphing it into something that we were more familiar with, as far as like a piston cylinder system, because obviously everybody's pretty familiar with those. You probably get around every morning in a machine that uses one of those. And so these are just a couple of the initial design sketches that we were looking at: having an intake both of them feature an intake and then an outlet through the back that the piston would obviously expel the water out of the back. And so we went about designing that and going forward with that design in CAD. Here's our initial CAD designs, and we knew it was going to be a 3D printed part, and so we went with a skeleton style design, which you can see on the bottom right, sensor mounting plate on the inside of the skeleton that would be modular enough to put whatever kind of sensor you wanted to on it. And then we figured we'd wrap that skeleton in a waterproof material like silicone or something like that. And then the nose cone is the thing that you see on the upper left, and it's in the upper right as well. And the nose cone used some mounting brackets to mount those wings that I was talking about earlier to control the direction of the robot. And then on the bottom left, you see a preliminary design of the propulsion system, which is a cylinder piston system that you can see there. And so once we had this all drafted up and we were looking at these renders and sketches of it, we realized we started to run into a couple problems and realized we had to address those. And so the main one that we realized is that after drafting all this up, it wasn't looking super bio-inspired anymore. And we kind of knew that was going to be a problem that we had to go back to the drawing board. We also realized the silicone wrapping was going to be more trouble than it was worth as far as just getting it cut out right and sealing it, because there's going to be the propulsion system and a linear actuator inside that needs to be watertight. And we realized that the wrapping it in silicone would prove to be too difficult, and we didn't want to have to run into problems with water leaking in and messing with the electronics and that kind of stuff. Also, again, with the same wrapping the skeleton and connecting the skeleton to the nose cone, we realized was going to be kind of a difficult task. And so we needed to figure out a way to cohesively design all these parts together and get them to seal together in a way that we knew was going to be waterproof and also was a little bit more cohesive. And the last one, we realized after we had received the linear actuator that would be used in the propulsion system, is that we would need to soundproof our robot, because the linear actuator makes quite a bit of noise. And like I said in the beginning of this presentation, quiet robot was one of the main goals. The bio-inspiration, being quiet and being modular. And so from here, we went back to the drawing board and iterated on the design, and I'm going to let Nick take over and talk about that a little bit.
Hi, I'm Nick Cornejo. I'm one of the group members that has been working on the skeleton and the body's shell design in 3D SolidWorks and as sketch drawer of the actual model itself. So we had to move away from our original design because our sponsors and us as well realized it wasn't very bio-inspired. So we were kind of having to remodel our design before we can actually get to prototyping. The model itself is still going to be a cephalopod, looking still into squids, but we're going to try and take more of their physical appearance and aspects of how they move around in the ocean to move into the newer model. As seen in this slide, the sketches use a two-shell design, piece design, and a skeleton frame on the inside, as well as gasket fittings that are going to be used to seal up the seams and to make sure that there is a minimal amount of water being able to get into the actual shell itself. Although most of the components inside of the shell will be somewhat water resistant. The shell design is going to be constructed of some from a 3D printer. The shell itself will be secured together with some smaller 2mm screws and to assure a good seal between the gaskets and the two shells. So as we're moving forward with this project, in this next slide, the this is what we're coming up with at this point of trying to get it to look more like a cephalopod and resemble the movement of a cephalopod itself. As you can see, we're using a wing design that is going to flap around to move left and right, to rotate the squid itself, to get different angles. And we're going to be using possibly a Picatinny rail on top and bottom of the robot to try and get good mounting points for a camera, temperature sensor, and possibly maybe a salinity sensor. And then, you know, there's a hole for wiring because we're going to be using buoy to control the robot itself, because currently we're going to be using a simpler design on the inner part of this robot because we thought it'd be too complicated to have every single component, and we wouldn't be able to maneuver the robot itself very well underwater if it was just automated, and it might cause some issues further on down the road as we go on finishing this project. The robot is going to be a two-piece design, as I said before. The wings will possibly be used. We will possibly be using a servo motor to be manipulating the wings up or down. And then there's going to be the linear actuator inside, which we'll see in a bit. That'll be sitting inside the shell within a skeleton until we finalize our design. And so we're going to be moving on to the next part. See, so this is our CAD design so far. What we've been thinking of is going to have a shell that we've designed already, and it does look like a squid somewhat. And so we're going to be using a smaller skeleton that's just going to be using the linear actuator. The linear actuator is going to be later on attached to the propulsion system, so that way we can have a final model here in the coming weeks, and so that way we can get moving on to prototyping. As you can see, it's a little bit more just of a simple design. It's way simpler than the original one because we're going to be, you know, moving away from having controls inside the shell itself and using a different form of movement for the robot and communication. With our design, we also have to take into consideration the amount of noise that's being produced by the linear actuator and probably the servo motors that we're going to have. So we conducted this test that will be that we tested the sound noise level of our linear actuator inside of a 3D printed box of the material we are going to be using, as well as using 3 different types of soundproofing material. One was a muffler packing, the other one was sound dampening mat, and then there was an acoustic foam. Both of these, or all 3 of these materials were somewhat noise reducing. There will be a recording of the experiment here done and talked about by our team leader, Connor Gorman.
All right, we're in the 360 lab right now, and we are running our experiment to test different soundproofings for our motor. Our setup is that we have our little actuator in this little black box here, and we put some soundproofing material. Right now we're doing soundproof foam. So we line the inside of the box with those materials. We're now screwing it tight, and then when we're ready to run it, once it's all the way on, we just hook it up to the battery and record with the sound device. And we can test the decibel level and see what kind of soundproofing we're getting. We're gonna make a graph comparing different distances and different materials.
Cool. And what's the importance of the material that the box is made out of?
It is the same material as what our robot's going to be. It's the carbon fiber nylon, yeah, that we're using to print the robot. So we're testing with the same material that we're gonna be using in the final robot.
So I'm back really quick just to talk about the conclusion of our soundproofing experiment and what we figured out in the lab testing all the soundproofing materials. The first thing we did is we calculated the coefficient of sound reduction of each of the materials at a 1 centimeter distance, just because there's the most variation in readings at 1 centimeter, obviously, because it's the closest to the motor. And so the readings were also the highest. So for the acoustic foam, we found that it had a coefficient of sound reduction of 0.63 The sound deadening mat was 0.85, and then the muffler packing material was negative 0.09, and the sound deadening mat and foam together, we stacked them on top of each other, was negative 0.42. And those, obviously the acoustic foam and the sound deadening mat were the most effective, sound deadening mat being more effective. And it's also a pretty useful material because it comes with adhesive on one side. It's usually used in cars to deaden sound from the engine or just from road noise. And so it comes with one side already adhesive, which is pretty useful for our purposes because we'll need to adhere it to the inside of the shell. The other metric that we looked at is the cost per area. And the cost for each of the materials. For the acoustic foam, it was 1.19 cents per inch squared. The sound deadening mat was 1.80 cents per inch squared. The muffler packing was the most expensive. It was 7.47 cents per inch squared. And the combo of the sound deadening mat and the acoustic foam was 2.99 cents per inch squared. And so the acoustic foam and the sound deadening mat on their own are the most affordable, with the acoustic foam being a little bit more affordable. And so going forward, we'll need to weigh our options as far as, do we want the sound deadening mat because it's more effective at insulating the robot to sound, but it's a little bit more expensive, or do we want to go with the acoustic foam being a little bit less expensive, but also a little bit less efficient with the deadening of sound? So that's it for Nick and I. Thanks so much for listening.
For our controls, we're using Arduino Megas, giving us plenty of digital and analog pinouts for anything we need. Megas are widely supported by the Arduino community, and we can easily add hats or shields to the Arduino for the control of the motors, the display, and the wireless communication to our buoy. The programming will be written up using the Arduino IDE, as our team has experience in that environment. The remote control and the robot will each have their own Arduino and leverage a 2.4 gigahertz Zigbee radio to communicate. The Zigbee radios have been around for a while and are also well supported. The remote control will be a custom handheld pendant, which will house a simple 4x20 serial display for showing the current command being given and the battery life. Directional control of the robot will be given using joysticks, much like thumbsticks found in the video game controller. When deciding to control a robot, you need to decide whether the robot will operate autonomously or if you will control it manually via remote control. Autonomous controls are really tempting, as it provides the ability for the robot to operate without any external wiring or transmitters. However, the tasks that the robot must perform needed to be very specific and laid out in clear sequences in order for a programmer to write the code to perform them. By taking this approach, we severely limit the number of scenarios the robot can be used in, as we can only account for so many possibilities. For example, if the customer was conducting research within a reef and wanted to change the path of the robot during the experiment, they could not without having to retrieve it and reprogram it. Furthermore, we eliminate the ability for the robot to adapt to unplanned circumstances, such as sea life interfering with it or currents throwing it off course, as we have seen with another popular autonomous robot, the Roomba. This type of automations can quickly unravel when an unexpected object is introduced into the path. Remote controlling alleviates these issues by allowing the customer to have total control of the robot at all times and have the freedom to adjust how it is piloted to suit almost any purpose. As use cases are further defined, we could go back and write autonomous programs for the specific needs. With autonomous operation out of the way, we began to think about how we could remote control the robot. At first, the simplest way forward appeared to be using an off-the-shelf hobbyist remote control like those that are used with RC airplanes. These types of remote controls operate using a very common 2.4 gigahertz frequency and can be obtained easily. We knew we would need something more complicated at some point, but this would be a good start for manually testing the propulsion and fin systems. However, before fully committing to the idea, we needed to investigate the range we would get with using 2.4 gigahertz radio. Over the air, 2.4 gigahertz radios are capable of achieving a range of up to 92 meters, but underwater is a lot different. It soon became clear that due to the conductive nature of water, we were going to run into trouble, and our intended environment, saltwater, is more conductive than freshwater. Because of the conductive nature, radio frequencies do not travel very far before the signal significantly degrades. The image shown is from a research paper written by Jamie Lorette, Sandra Sendra, Miguel Ared, and Joel Rodriguez, titled Underwater Wireless Sensor Communications in the 2.4 GHz ISM frequency band. Their tests using the 2.4 GHz bandwidth showed that with freshwater we could only expect to achieve 15 centimeters before the signal began to degrade, and by 18 centimeters, the signal would experience total packet loss. So with this in mind, the 2.4 gigahertz range was out of the question if we wanted to transmit underwater. We then began to research lower frequencies that tend to transmit better underwater. These frequencies are typically under 30 kilohertz, but we were finding those transmitter-receiver combos to be much more expensive and the speed at which they transmit to be much slower than the 2.4 gigahertz counterparts. Even if we were able to obtain a low-frequency radio that we could implement into our controls, we would likely see latency when attempting to control the robot. This latency could lead to either losing or damaging the robot. Without a clear way to move forward with our remote controls underwater, we began to look at what some other submersible robots used and came across the idea of a buoy. The idea of the buoy is that it would sit on top of the water with a retractable cable connecting it to the robot. Not only does this allow us to remote control the robot using a very easy to find 2.4 gigahertz radio, but it allows us to keep the very heavy battery out of the robot and keeps the electrical controls above water. The retractable cable will be able to spool out extra cable while the robot moves forward further away from the buoy and retract the cable as it came closer. This should minimize the risk of tangling the tether on cable on objects in the water while also providing a means of retrieving the robots should something happen to it.
After discussing and collaborating with our sponsors, we got a better feel of what they are looking for in a robot design, and we've improved our focus on bioinspiration. We have iterated upon our initial design, making changes to fall more in line with the customer's needs, and created something that they both approve of and are interested in seeing us complete. We are in the process of finalizing the body of the robot and the controls of the robot in order to get the model into the prototyping phase, and we have a clear plan on how to get there now. While going through the design phase, we have noticed that meeting consistently with our customer is important to keep them in the loop of the important design changes that we have made in case they don't approve or have concerns about that robot, as well as providing them the opportunity to weigh in on the design choices in case, they want to make a quick change before we move too far forward with the design of the robot. The prototyping phase will require a lot of work from our team, and we expect our designs to adjust as we continue to improve the robot. We are excited to move forward and present a final version that we are proud of as a team. Thank you.